Dear students, today we are going to learn haloarenes, chemical reactions and their properties. Usually, haloarenes undergoes electrophilic substitution reactions. They are commonly halogenation, nitration and sulfonation, Friedel-Crafts reaction, which is alkylation as well as acylation. Whereas nucleophilic substitution reactions of these compounds are very rare and it undergoes under very specific reaction conditions. And the third category of reactions haloarenes undergoes are reaction with metals. Under this we are going to learn about Wurtz-Fittig reaction and Fittig reaction. And after this we are going to focus on polyhalogen compounds, that is the compounds which are having halogens, for example dichloromethane, chloroform, iodoform, freons and DDT. Yes students, let us see the chemical properties of haloarenes. Yes, let us take chlorobenzene. This is the chlorobenzene, right? So nucleophilic substitution, is it easy to undergo nucleophilic substitution of this chlorobenzene? Chlorine is a minus I affecting group. That means it pulls the electron density towards this side, one thing. And however, the second factor and important factor of this chlorine is it also has lone pair of electrons which resonantly stabilizes with ring. That means it back donates towards ring and it is going to form nucleophile at ortho position, and further resonance it is going to form nucleophile at para position. So it is not easy to remove this double bond by substitution. Nucleophilic substitution, it is not going to take place with respect to haloarenes. So when it comes to haloalkane, we have seen that nucleophilic substitution SN1 and SN2, whereas aromatic halo compounds, it is not possible or it is tough to undergo aromatic nucleophilic substitution. Why? Because the CX bond or the bond between carbon and halogen is sp3 hybridized carbon. That means the electronegativity compared to this sp2 hybridized carbon is less, and in this haloarenes the bond is the carbon is sp2 hybridized, so the sp character is about 33%. Because of this 33% of s character, it is highly electron negative character is more when it compared to sp3 hybridized carbon. So it is not easy to break this double bond type of character, or it is not easy to undergo nucleophilic substitution. And instability phenyl cation. Imagine somehow it forms phenyl carbocation. This is phenyl carbocation. Is it stable? This is phenyl carbocation. Is it stable? No, because it is not aromatic. Because of instability of phenyl cation and difference in hybridization of carbon atom in CX bond and resonance effect, these haloarenes usually do not undergo nucleophilic substitution. So when some nucleophile wants to attack this carbon, this is nucleophilic substitution, where if someone wants to substitute this chlorine atom with nucleophile, and the incoming nucleophile also will have electron pair. So this electron pair is going to repel. That is why nucleophilic substitution is not observed in haloarenes. But however, we come across few reactions. For example, replacement by hydroxyl group, where treatment of this chlorobenzene with sodium hydroxide at high temperature under pressure. Usually what is that? Atmospheric pressure. At room temperature it is 1. So you are forcibly making to undergo nucleophilic substitution. That means the incoming nucleophile is OH minus is forcibly replacing this. So to make it possible at a low temperature, haloarenes are substituted with nitro group, either ortho or para. It is going to undergo this nucleophilic substitution very easily. For example, it is substituted at para position, say 443 K, means it is around, if I remove 300, it is around 150 degrees centigrades. So doing 150 degrees centigrade reactions at room temperature is is common. And when it comes to substitute with two nitro groups, especially at ortho and para, it is going to be very easily removable or substitutable with nucleophile of OH minus. When it is substituted more number of these nitro groups, just warm means just 40 degrees is enough to undergo this reaction. So just now what I said, nucleophilic substitution is usually not possible, but when the ring is substituted with nitro group, it is easily allowing the incoming nucleophile to substitute chlorine group. If you take this chloro compound, when it is substituted with the nitro group at ortho position, the incoming nucleophile, this is a hydroxy group, easily replaces this chlorine. Chlorine is going out. Why? Because the incoming nucleophile is going to form nucleophile or anion at this. So nitro group is going to stabilize this anion which is formed during the nucleophilic substitution with sodium hydroxide or hydroxyl group. When it is para, same thing is going to happen. What is happening? The negative charge which is formed here, it is going to be stabilized. So this nitro group stabilizes like this. Yes. So because of this stabilization, the chlorine is easily substituted with hydroxy group. Same thing when it comes to meta position. So during the resonance stabilization, it is not going to form negative charge at meta position. Do you observe negative charge at meta position? This is meta position. No negative charge. In all resonance forms, there is no negative charge. So this nitro, though it is having nitro substitution at meta position, it is not going to have any effect. So nucleophilic substitution of meta substituted nitro compound is very tough. Halogenation, nitration, sulfonation and Friedel-Crafts reactions. Yes, so the orientation of haloarenes is ortho and para. How? See, let us see. So because of this lone pair electron, it is going to resonantly stabilize and it is going to form ortho position negative charge. So it is negative charge, and the incoming reagent, what it should be? It should be electrophile. It should be electrophile, right? So electrophile, because it is having electron excess, so it wants to react with electrophile. It wants to give this negative charge to electrophile, which is electron loving species. So it reacts with electrophile and forms ortho and para. So when you do the halogenation with chlorine and anhydrous ferric chloride, it undergoes aromatic halogenation. Yes, what is happening? It is going to give two products, mixture of two products. What is this? One is monochloro, that is ortho chlorobenzene. It is parachlorochlorobenzene, R14 dichlorobenzene and 12 dichlorobenzene. So here it is written as para is major and ortho is minor. Why? It is very simple, students. So since it is a chlorine group, so the incoming chlorine group, it is very tough to approach the ortho carbon. That is why, though it is forming, it is minor compound. Minor means you are getting very few percentage of ortho product, but the para position, yes, it can attack very easily. This carbon is very easy to attack. So para-chloro dichloro compound we are going to get. Same thing holds good when it comes to nitration. Nitration also. Yes, students. So major, what is going to form? Para nitro, because the incoming nitro group, what is the electrophile here? Nitro group NO2 plus. It is going to be formed from HNO3 plus H2SO4 sulfuric acid. So the incoming electrophile, this easily attacks onto ortho position and para position. Para is major because the nitro group is very bulky group. Already chlorine is here. When it wants to come, it is tough, though it is forming, facilitating the entry, but this chlorine group which is there already, it is not going to allow because of this repulsion. It is repulsion, so there will be tough to approach here, whereas this para position, it is free to enter. That is why the formation of para compound is major. Yes, students, and here I want to ask a question. Suppose if I want to make this para nitrochlorobenzene, it was asked in 2020 NEET. Yes, so if I want to make this para nitrochlorobenzene from benzene, what is the route you propose? If I make nitrobenzene first, if I make nitrobenzene here, so nitrobenzene is formed. So nitrobenzene, when I want to do chlorination, yes, chlorination, I can take chlorine in ferrichloride, chlorine, iron chloride. So what is going to happen? This nitro group is meta-directing group, but when you are required is with para-chloronitrobenzene, then what will you do? So you are going to get meta-chloro. So if you are asked to make this from benzene, it is the way to make is first make benzene to chlorobenzene, this chlorobenzene by simple chlorination. In presence of iron chloride, you are going to get chlorobenzene. This chlorobenzene upon nitration, you are going to get this para-nitro. Whether it is bromo, it can be bromo, it can be iodo. Yes, doesn't matter. These chloro, bromo, iodo compounds are ortho-para directing groups. That is how you can make this halogen substituted nitro compounds. Sulfonation, so same thing, sulfonation also, it is also electrophilic substitution reaction. Na2S2O7 or H2S2O7 is oleum. This oleum mixture fuming sulfuric acid is going to undergo this sulfonation. Usually concentrated sulfuric acid, even if you heat for at high temperature, it is not easy to undergo this sulfonic compound. These sulfonic compounds are like char-like compounds, right? So what is happening here? Also para position is going to be major product. Friedel-Crafts reaction, and moreover it will involve 3 steps. Generation of electrophile. So this chloromethane plus anhydrous aluminum chloride, it is going to form generation of methyl cation. This is electrophile, generation of electrophile. Yes, and aluminum chloride is going to be AlCl4. So this is the first step, and the second step is generation of intermediate. This is going to attack onto this methyl group to give, and it is attached to methyl group. So carbocation is stabilized by this lone pair of electrons. So I can stabilize or resonance this side, or this side. Wherever I want, I can put this 2, 1, 2, 3, 4, 5. 5 carbons are going to share this carbocation, this positive charge. So transition carbocation intermediate. Then what is the third stage? So removal of hydrogen. To give product. In this case, it is going to give chloro. So it is because of this aromatic nature, it is going to lose plus or H hydrogen ion to give methyl. So this is how all electrophilic substitution reactions involves generation of carbocation and transition state and removal of hydrogen, whether it is chlorination, nitration, sulfonation or Friedel-Crafts reaction. So this is Friedel-Crafts alkylation. Here also what is happening? So para is going to be major, right? So major is para. So acylation also is going to take place. The carbocation is acylium ion. So this chlorine is going to out, and it is going to react this double bond. It is going to give ortho and para, and here also para is major. Then how will you separate these 2 compounds? Do you have any idea? Usually these ortho compounds are steam volatile, and because of this hydrogen type bonding, so this is oxygen and chlorine, it is going to form this hook like bonding, and it is going to have low boiling point, and it is going to form hydrogen bonding. So it is easily removed at a low temperature, and whereas this parachloroestophenone remains in the reaction vessel. Next, let me ask questions. Although chlorine is an electron withdrawing group, just now I have explained, yet it is ortho and para directing group. Electron withdrawing group, for example, if I take nitro compound, nitrobenzene, what is the orientation of nitrobenzene? It is meta directing group. So the electrophilic substitution takes place at meta position. So they are asking, so it is also like electron withdrawing group. Yes, electron withdrawing group chlorine. However, it is undergoing electrophilic substitution, and it is directing ortho-para contrary to its electronegativity. The reason is, though it is electron withdrawing group, it is pulling the electron density of benzene ring towards it, but the resonance stabilization or back donation of this lone pair electrons is major, right? Attack at ortho position is stabilized by back donation of this lone pair of electrons. This resonance stabilization because of mesomeric effect of this. So what is going to happen? Though inductive effect is destabilize the intermediate, carbocation formed during the electrophile substitution is going to be stabilized by its lone pair of electrons. That is why it undergoes electrophilic substitution and it directs the incoming electrophiles at ortho and para. So nitrobenzene, when I do chlorination, it is going to give this. Next. And haloarenes, what I said, the third category of reactions haloarenes undergoes are Wurtz-Fittig reaction, and this is nowadays we are not doing, though it is very important to do. Alkyl halides, sodium and aromatic halides in presence of dry ether. What is going to happen? It is going to take out this halogen and this sodium with this halogen. It is going to out and it is going to give alkylated aryl compounds. Yes. So the yields are very poor with respect to this reaction because there is a chance to undergo self-Wurtz reaction because this alkyl halides self-coupling takes place to give alkane, and there is a chance to form diphenyls also, diphenyls like this. So it is a mixture of three products you are going to get Wurtz-Fittig reaction. To overcome this, so there is a way to make these compounds is Fittig reaction, where you can take only aromatic halides, and when you do the sodium reaction in dry ether, it is going to give diphenyls. So this is very important reaction in organic chemistry where you can prepare diphenyls. Yes students, so this is how it is. Aromatic arenes are going to undergo this Fittig reaction. Yes students. So which alkyl halide from the following pairs would you expect to react more rapidly by SN2 mechanism? Explain your answer. So SN1 is favorable in tertiary alkyl halides, whereas SN2 is favorable in primary alkyl halides. SN2, so the primary alkyl halide going to react more fast, and here this is not at all undergoes SN2, it undergoes SN1, right? So this is, though it is secondary, there is a chance to undergo SN2 reaction. When it comes to this, so though it is primary and it is also primary, but it is when you look from this side, it is very near to this secondary carbon. So this is going to undergo SN2 very easily when it compared to this compound. In the following pairs of halogen compounds, which compound undergoes faster SN1 reaction? Just now what I said, SN1 reaction tertiary alkyl halides easily undergoes tertiary alkyl halides. So this is easily undergoes. When it comes to this, it is going to be SN1 secondary alkyl halides when compared to primary alkyl halides. SN1 takes place. Then, so this is very important students. Find A, B, C, D, E, R prime. So this type of questions you are usually going to get in board exams as well as in NEET and JEE or whatever may the entrance exams. So don't worry, just now what I said. So alkyl halide, when you treat it with magnesium in dry ether, what is this A? You are going to get Grignard reagent, organometallic compound. Alkyl magnesium halides or aryl magnesium halides are known to be Grignard reagents. You are going to get Grignard reagent. So this Grignard reagent, when you treat it with water, it is going to form hydrocarbon or alkane, cycloalkane. So it is a common side reaction. If you have any moisture or air or water, so this reaction or Grignard reaction is going to spoil and it is going to release this alkane or this hydrocarbon. That is why Grignard reaction must be done under extreme dry conditions. Yes students. Next, so same reaction, alkyl halide in presence of magnesium, when you treat it with dry ether, it is going to form alkyl magnesium halide. This alkyl magnesium halide, when you treat it with deuterated water, D2O, you are going to get deuterated product. Yes student. So they have given this propane, so they are asking what is R. So R is, so it is going to form alkyl magnesium halide, and this alkyl magnesium halide, it is going to give deuterated compound. This is one of the ways to prepare deuterated alkanes. So this is what is happening. This is R prime X. When you do sodium ether, what is the reaction? Wurtz-Fittig reaction. Wurtz reaction, you are going to alkane. So in 2020 NEET, it is asked. So is it easy to make odd number carbon containing alkanes by Wurtz reaction? No, because it is going to form dimer of, even if I take mono or one alkyl or ethyl chloride or butyl bromide or whatever with the compound, odd plus odd also gives even number of carbons. Even plus even carbon containing halogens also going to give even number of carbons. So the answer is odd number containing carbon containing compounds by Woods reaction is not going to be prepared or not going to be formed. So here what is the reaction? So please concentrate students. Here what they have taken, though it is tertiary alkyl halide, it is going to undergo Woods reaction. This is tertiary alkyl halide, tertiary butyl. If it is bromo, it is tertiary butyl bromide. It is undergoing this Woods reaction to give this product. When you treat with magnesium, yes, this is also tertiary butyl magnesium halide is going to be formed, and this upon hydrolysis you are going to get tertiary butane. Halogen containing compounds, the common compound in laboratory you will come across is dichloromethane. Dichloromethane is used as a solvent in organic chemistry. So when it comes to chloroform, chloroform also previously used abundantly as a solvent in organic chemistry, but now it is also banned and it is rarely used. And moreover, as a solvent, previously it was used as anesthetic compound because the chloroform which is there is going to react with oxygen in presence of light. It is going to form highly poisonous compound phosgene. And triiodomethane or iodoform, previously it was used as antiseptic, but nowadays it is not used because advanced better compounds are available. Yes, right? When it comes to tetrachloromethane, carbon tetrachloride also is very common solvent in organic chemistry, bromine in CCl4. Yes, so CCl4 is used as common solvent. It is used huge amount for the preparation of refrigerants, freons and general organic solvent and cleansing fluid, and even it was allowed to use as fire extinguisher at home. And freons. So freons are highly objectionable compounds where these freons, when it goes into stratosphere, and these upset the natural ozone balance. So these freons are very highly objectionable compounds which are halogen compounds. So chloramphenicol for the treatment of typhoid, and haloform is for the anesthesia, thyroxine for goiter, like that. However, there is an antiseptic compound which is DDT. So the common name is DDT, which is nothing but para. This is para position. With respect to this is para position. Para dichlorodiphenyl, because this is diphenyl. Trichloroethane, trichloroethane is DDT. It is commonly used as insecticide where it kills or it repels mosquitoes and lice that carry typhus. Bye, sayonara. We'll meet again with new topic. Bye till then.